Yeah, hello everyone. Well, thanks for coming to my talk. My name is Timur Doumler, also known as Timur Audio on Twitter. I'm C++ developer advocate at JetBrains. We make the C-Line IDE and other C++ tools. Um, I'm actually here for the first time at NDC TechTown. It's very exciting to be here. And I have a couple days ago agreed to this slightly crazy thing of doing 3 talks in a row here. So it's a bit of a talk marathon. It's all going to be in this room. This is the first one of them. And it's by far the most niche and specialized topic out of the 3 talks. So it's interesting to see so many people turn up. I hope you're not going to be too disappointed. This is a 60-minute version of a 90-minute talk that I gave a couple months ago at C++ Now. And it's about a lock-free atomic shared pointer. Now, you might ask yourself, why are we still talking about shared pointers in 2022? We learned that it's global mutable state. That's a bad thing. We shouldn't be doing this. We should be doing value-based programming, and then everything becomes fine. Yes, totally agree with that. But atomic shared pointer actually has, it's a kind of more specific thing which has very interesting use cases. And so first of all, when you talk about shared pointer itself, who has been to the talk just before this one in room 1, Hanna Dushikova, lightning updates? Okay, a few people. So she mentioned this. If you make it a shared pointer to a const object, then the whole problem of mutable global state kind of goes away. But that's not what we're going to talk about. We're going to talk about the atomic shared pointer part. And that is also very useful. In particular, if you have objects that you need to share across threads. And in particular, if you need to manage the lifetime of those objects across threads. So you want to avoid scenarios where one thread is deleting an object and another thread is still accessing it and stuff like that. So atomic shared pointer gives you a very nice solution for that. And if you've been to Hannah's talk just now, she actually had an example for that. She actually was using that in her code where she was doing exactly this. And you want to do it in a lock-free way if you are on some kind of time-critical, low-latency, time-constrained system. You don't want to use a mutex there. You don't want to wait on a mutex. You don't want to run into the priority inversion and things like that. And also this topic of kind of lock-free atomic shared pointer actually comes up when you're not just sharing objects across threads in a lock-free way, but using lock-free structures, lock-free data structures. That's something that kind of often happens. So you have something like a lock-free queue or a lock-free stack, things like that. And it turns out there are kind of multiple ways to implement those, and usually it gets very, very, very complex. But like there was this talk by Fjodor Pikus a couple years ago where he identified pretty much 3 kind of basic building blocks that you can use to implement lock-free data structures. One of them is RCU, read, copy, update. Another one is hazard pointers, and a third one is the atomic shared pointer. And they all have different trade-offs, so you might want to use one or the other or the third, depending on what exactly you're trying to implement. An atomic shared pointer is obviously the one that we are going to talk about here, and it has some interesting properties. In particular, if you have a lock-free implementation, both reading and writing can be lock-free on as many threads as you want, basically simultaneously, which is a very interesting property. And here's a paper by Herb Sutter, which was the motivating paper for putting atomic shared pointer into the standard. And here he mentioned as the motivation ABI robustness and efficiency. And the ABA problem is something that you run into immediately if you're trying to implement a lock-free structure, lock-free data structure in C++. It's basically this thing of, you have an object and then that gets removed, but then another object gets placed into the same memory, and then the other thread cannot tell that the object actually has changed, and then everything just explodes. And it's very, very complicated to get around that problem. If you look into, for example, real-world implementations of kind of a multi-reader, multi-writer lock-free queue, like Boost lock-free has one, Moody Camel has one, and you look into how they're implemented, and you're going to see that they're horrendously complicated. It's just really like load, store, all these operations have these like really, really long implementations with really complicated cast loops in them. And it turns out this complexity comes from basically 2 things. A, you need to manage the lifetime of your nodes, your elements, which is quite complex across threads. And B, you need to account for the ABA problem, which is very, very complicated to do in C++. And it turns out atomic shared pointer kind of really nicely encapsulates both of those problems, because obviously, atomic shared pointer manages the lifetime of the objects, so you kind of solve that problem. And then also, atomic shared pointer doesn't really suffer from the ABA problem because shared pointers are aware of the identity of the object that they're pointing to, right? So if you have another shared pointer, even if the object it points to lives in the same memory, it's going to be a different object with a different shared pointer pointing to it. So you don't have this ABA problem because shared pointers are aware of the identity of their objects. And it turns out that if you use that as a building block, then lock-free programming becomes a lot more kind of easy to reason about. And so here's an example from Herb's paper where he's implementing a concurrent stack. And you can also do this with the queue. It's going to be pretty much the same size of code, more or less. So what this does is it's a concurrent structure that supports pop and push. It's a stack, so it's pop front and push front. And then it also supports find, so you can find an element, and you can do any of those things simultaneously from as many threads as you want. And it's just going to work. And the whole thing fits on a slide, and this is the complete working implementation. Okay, so that's pretty cool. And the secret here is this atomic shared pointer. That's the thing that makes it possible, because it kind of encapsulates like this whole complexity. And this is not necessarily the fastest implementation you can come up with. If you write everything out by hand, probably you're going to be, and you're tweaking it to a use case, you're probably going to end up with something a bit faster. But this is very easy to reason about, and it's very useful kind of as a building block. And yes, and you want this to be lock-free if you're on a time-constrained system. So we're going to look later into how to achieve that. Before we do that, let's briefly talk about shared pointer. So we have three parts here, right? We have shared pointer, atomic, and lock-free. And I'm going to talk about all three. Obviously, let's start with the shared pointer. If you're here in this room, I assume that you all know what a shared pointer does. So I'm just going to extremely briefly go through this. This is what the C++ standard says about shared pointer. It's a smart pointer that stores a pointer usually obtained via new, so it's something that lives on the heap. And it implements semantics of shared ownership. And the last remaining owner of the pointer is responsible for destroying the object. So basically, it implements ref count and implements kind of deterministic cleaning up of objects using ref count. How does it work under the hood? Here's like a very bare bones minimal implementation of a shared pointer. Basically, the shared pointer itself, it's just this pointer to a control block. This is the thing on the left. And the thing on the right is the control block itself, which contains a pointer to the object that the shared pointer is managing. It contains a reference count, ref count, which in this case is 1 because we have one shared pointer that's pointing to it. And then we have the object itself. That's the yellow blob. And depending on whether or not you allocate this with make shared or not, the object might or might not live in the same block of memory as the whole control block. And now what we can do is we can copy the shared pointer. We can create a new shared pointer pointing to the same control block. And then that's going to increase the ref count, right? So now the ref count is 2. We can delete that shared pointer object, or like it will go out of scope somewhere, and its destructor is going to be called, and then the ref count is going to decrease again to 1. And then if that one last shared pointer instance is also eventually going out of scope, then the ref count is going to reach 0. And as soon as that happens, the control block is going to actually deallocate the object, and then it's going to deallocate basically itself. And again, if you allocated this with make shared, then this whole thing will be a single deallocation. So this is basically how, oversimplified, how a shared pointer is implemented. And now you want to make this atomic. Okay, so that's the next thing we need to do. What does atomic mean? Atomic basically means it's thread safe, like you can operate on it from multiple threads, and there's not going to be a race condition, right? This is pretty much what atomic means. So it's basically thread safe. The C++ standard doesn't really say very much about whether or not shared pointer is thread safe. It says this sentence here: changes in use count, which is the ref count, do not reflect modifications that can introduce data races. This is all it says about that. So what that means is if you have a shared pointer and you have a ref count of 1, and then on one thread you make a copy, and then the ref count is 2, and then on another thread you make another copy, and now the ref count is 3, both threads are going to agree that the ref count is 3, and you're not going to have a data race. And this is achieved by having the ref count be an atomic counter. right? So this is basically how this works. This is how a shared pointer works. Hopefully this is not too surprising for anybody here. Is this actually thread safe, right? So let's look at this. So we have a shared pointer we created with make shared, and then, as you already said, we're making a copy of that on one thread, and we're making another copy of that on another thread, and that is fine. As we just saw, the ref count is atomic, it's fine. What happens though if we flip this around on the second thread, and now on one thread we copy the shared pointer, and on another thread we are assigning a new object to it? Or rather, we are assigning a new shared pointer to it. So we are copying on one thread and we are assigning to it on another thread. Is this thread safe? Who thinks it is? Who thinks it's not? Yeah, this is a data race. This is undefined behavior. And actually, if you think about it, it's not very surprising because it actually behaves exactly like an int, right? If you have an integer, you can copy it on one thread, you can copy it on another thread, and that's fine. But if you copy it on one thread and you read from it, if you copy it on one thread and you assign to it on another thread, that's a data race, right? So you need to make it an atomic int in order for that not to happen. So it's the same thing as with an int, really. And this problem, has been well known for a while. That shared pointer isn't thread safe, really. You can't use it in this multi-threaded environment that we're interested in, like the stuff that Hannah was showing, for example, in the previous talk. So since C++11, actually, since we had shared pointer in the standard, we also had this stuff in the standard, which are these weird kind of freestanding functions that allow atomic operations on shared pointer. So we had these since C++11. They're probably not very well known. It's these freestanding functions, and they always have the name atomic underscore whatever operation, load, store, compare, exchange, etc. And then you pass a pointer to the shared pointer that you want to operate on as the first argument. So it's like a really awkward kind of non-C++ C API that we had now for a while. And that's kind of all we have in the standard, really, and all we had in the standard. And you would use it like this. So this is what we had to do before C++20. Instead of copying it and then assigning it, we would have to do an atomic load on one thread, which is the copy, and then an atomic store, which is the assignment on another thread. And if you do this, it's thread safe. However, it's not a great solution. First of all, because they're freestanding functions, you can't really efficiently implement that. That's kind of more like an implementation problem, because you can't keep the state that you need to keep track of the multi-threaded stuff with the shared pointer. It's a freestanding function, so it needs to operate on any shared pointer. So you can't really efficiently implement this. But actually, the bigger problem is that it's not safe to use. It's unsafe by default, right? If you have a shared pointer, you copy it, you assign to it, that's not thread safe. You have to remember to use the atomic load and atomic store instead to make it thread safe, right? And if you forget to do these freestanding wrapper functions, even on one thread in one place, you just use the normal assignment or copying, then your whole program is undefined behavior because you have a data race, right? So it's really not a good API. And so coming back to this paper by Herb, who proposed to make atomic shared pointer a thing, so it's an object and you have everything in there, we now got it in C++20. So atomic shared pointer now is in C++20. And with that, it becomes a lot easier. So now instead of declaring a shared pointer, you would declare an atomic shared pointer. And then you can load it on one thread and store into it from another thread. So it's the same API as a normal std atomic. And that is now thread safe since C++20. So that's great. And you don't actually even have to write the load and the store. You can just omit that because the API is just like a normal std atomic. So you can just write this naked copying or assignment. And it's going to do the atomic thing under the hood. So it's safe by default, which is much better. I still prefer to do it like this because I still prefer to be explicit about, hey, this is an atomic operation, but it's a matter of code style, right? And the other great thing about atomic shared pointer is now that it allows more efficient implementation. So for example, if you're doing this with a mutex under the hood, which we're going to come to, we don't want that, right? We want lock-free, but the naive implementation is to do it with the mutex. if you have these freestanding functions, you can't store the mutex with the shared pointer, right? Because you can't store any state. So you have to have some kind of either like a lookup table where you have one mutex per shared pointer, or you just have a global mutex for all the shared pointers, which is apparently what the freestanding function implementations, or at least some of them, were actually doing. So it's super inefficient. With the atomic shared pointer, you can put this additional state that you need to make it thread safe into the atomic object itself. So you can actually implement it much more efficiently. And actually, both GCC and MSVC already ship this. Clang doesn't yet, but both GCC and MSVC in the latest version, you get the atomic shared pointer there in C++, if you're in C++ 20 mode. So that's great. And that was me. Before the latest standard came out, I was like, okay, great, we standardized atomic shared pointer, and surely it's going to be lock-free as well, right? Because that's what you want. Because if you're in a time-constrained system, if you're doing kind of low latency programming, you don't want to be messing around with mutexes. That you want to have a lock-free implementation. And it turns out, no. So I posted this on Twitter, when it was discussed before C++ 20 came out. I think it was early 2019. And I was like, hey, C++ standard library implementers. Hello, committee friends. Surely you're going to ship a lock-free implementation of this, right? And then STL, who is the maintainer of the Microsoft library, said, no. And I don't even think it can be implemented, right? Because how do you copy the pointer and increment the ref count all at once in one atomic operation? That's not possible. So I don't think this is implementable, so we don't do this. So our atomic shared pointer is doing exactly what the freestanding functions have been doing since C++ 11, which is using mutex under the hood, right? So, and indeed, if you do this on MSVC or in GCC, and you use these functions here, is lock-free. This is the per instance version, and then the is always lock-free, which is the kind of static compile time version. Both of them are going to tell you false. It's not lock-free. It's containing mutexes inside. So, if you're in a system where you want to be doing lock-free programming because you're in a tight timeline, and you want to have this kind of lock-free guarantee that at least one thread is making progress all the time, you can't use this, right? You can't use the standard library implementations, which is sad. So that was going on. And at the same time, there was Further, who already in 2017 was giving a talk about this and said, oh yeah, atomic shared pointer. Yeah, it's one of those, things that you can do here. And of course, like, it's lock-free, and, obviously I have an implementation of that lying around. And there's actually Anthony Williams as well, who wrote the book about concurrency in C++ in action. One of the, I would say, godfathers of concurrency in C++. And he published a blog post a while ago. He has this just thread library, which contains lots of concurrency tools. And he was saying, well, yeah, so you can like have a lock-free implementation. It's a bit more complex, but it's worth it because it might be slower in the uncontended cases, but when you have contention, you get this guarantee that it's lock-free, which is a very nice property. Therefore, my library ships with the lock-free atomic shared pointer implementation, right? So on the one hand, I have these standard library implementers who were saying, this is not implementable. And on the other hand, I have these other people like Further and Anthony, which are experts in concurrent programming, which are saying, well, yeah, you should use the lock-free implementation. And by the way, I have one. It's closed source, so you can't look at it, but I'm using it. And I was like, both of these things can't be true at the same time. Either it's implementable or it's not, right? So I would really want to see how this works, but where's the code? So I was in this dilemma for a while, and then I was like, okay, I need to do some research here. I need to like figure out what's actually going on here. Is this implementable or not? How does this work? And that's kind of what led me to, that was kind of the motivation for this talk, essentially. So status quo as of today, as I said, MSVC and GCC both ship with a non-lock-free implementation of atomic shared pointer. Clang just doesn't have an implementation. I don't know if anybody in Clang is working on one. But it turns out that actually there are 3 open source implementations of atomic lock-free shared pointer that you can look at today. So Anthony Williams actually published a version of his atomic lock-free shared pointer. It's not the one that he has in his Just Thread library, which is like the commercial production-ready version. It's more like a stripped-down kind of proof-of-concept version that shows the algorithm. But you can look at it. Then Folly, which is Facebook's C++ library, has an implementation of atomic shared pointer, which is also lock-free, and you can also look at it. It was written originally by Dave Watson, who since left Facebook. It's now maintained by somebody else, David Goldblatt. And then actually I found a third implementation, which is also open source and you can also use, by Vladislav Tulbashev. And he was basically looking at Anthony Williams' implementation. He was saying, well, I don't like this. Like, it's using double with compare and swap. It's too slow. And then he was looking at the Facebook implementation, the Folly one, and he was like, I don't understand this. And then he was like, I'm going to write my own. So he did that, and you can look at that as well. And I looked at all of 3 of those quite extensively and tried to understand what's going on there, and also exchanged quite a few emails with all of these people. And that was very helpful. And actually, Vladislav also wrote himself as well a blog post about how he implemented this, which is a very, very interesting blog post, which I very recommend you to read, except it's in Russian. So I can read it because it's my mother tongue, but you can't probably. So maybe use Google Translate. I hope that's possible. I think that's a really cool blog post where he's kind of going through the experience of implementing this. So how can we implement this? Is this actually implementable or not, and how can we do this? And this is kind of what we're going to look at. So the problem is, why did STL and the other standard library people say, I don't think this is implementable? Because we have this fundamental problem here. The shared pointer, the state of the shared pointer, is basically the pointer to the control block, which contains the object, and then the ref count. Right? Those are the 2 things that determine the state of the shared pointer. And if you want to make this atomic and lock-free, we need to mutate both of those values at the same time in one atomic lock-free operation. Okay? But they live at different memory addresses. They're not adjacent to each other. Like, one lives in a shared pointer instance, the other one lives in the control block. So they're like in completely different memory addresses, but you need to change both of them atomically lock-free at the same time with one CPU instruction, which is something that's called double compare and swap. And it turns out there's actually exactly one CPU that supports this operation, which is the good old Motorola 68000. So that CPU supports double compare and swap. On this particular CPU, implementing a lock-free atomic shared pointer is actually pretty easy. Unfortunately, no modern CPU supports this operation. So you cannot do this. You cannot lock-free atomically with one instruction modify 2 separate memory locations at the same time on Intel or ARM or like any of these like more modern chipsets. What those chips do support is something that's called double width compare and swap, which is not the same as double compare and swap. And double width compare and swap is basically modifying 2 words atomically lock-free at the same time, but only when they're adjacent to each other. So you have like if you're on 64-bit, it's going to be 128 bits. And you can modify a field of 128 bits at the same time, atomically lock-free in one CPU operation. Unfortunately, the control block pointer and the ref count are not adjacent to each other. So how can we make this work? And it turns out there is actually an algorithm that makes that possible. It's called a split ref count. And it's not something that you typically find in like a computer science textbook. So David Goldblatt, who is the maintainer of the Folly implementation, said, it's sort of a folk algorithm. It's like there's a few people on the planet who know how this works, and it's kind of passed down from one person to another. I actually found 2 pieces in the literature where this algorithm is mentioned. One of them is Dmitry Vyukov's blog about differential reference counting, and another one is Anthony Williams' brilliant book about C++ concurrency. Both of them mention the split ref count idea, but not in the context of implementing a shared pointer. So it's not quite the same thing, but it's kind of the same idea. So it is mentioned in the literature. People are doing it, but it's just kind of a little bit more obscure. It's not like, merge sort or something, which a lot of people are kind of aware about. So it's not that you can find lots of implementations of this everywhere on the internet. But you can find this in every one of these 3 implementations that are open source. And there are at least 2 more implementations that are not open source that I'm aware of. There's one big company that has a closed source implementation that I can't look at. And then there's Picos, who also has his own implementation, which is a little bit different. It's kind of an intrusive shared pointer. But it also uses kind of the same idea, kind of split ref count. So there are implementations of this out there. And at least 3 of them are open source. How does this work? The basic idea is that instead of one ref count, we basically split the ref count into 2 things. We have a local ref count, which lives with the shared pointer, and then we have a global ref count, which lives in the control block. And so what we can do atomically is we can modify the control block pointer and the local ref count simultaneously. And then we try to synchronize the local ref count with the global ref count in an additional step. So how does this work? Here's a little bit of code. So if you want to implement our atomic shared pointer, we're going to have this counted pointer structure in there, which is basically exactly this. It's a control block pointer and a local ref count, and this is our double width thingy that we want to double width atomically swap later. And then so we have an atomic instance of one of these, and then we need to assert that it's lock free because we don't want to use mutexes in there. And then here's the basic idea of this algorithm. So we cannot atomically update the control block pointer and increment the global ref count at the same time. So this is for the case when you want to load the shared pointer. We need to increment the ref count. But what we can do is we can atomically increment the local ref count, or we can atomically change the pointer and increment the local ref count. So that's step 1, incrementing the local ref count. And then in a separate step, we're incrementing the global ref count, and then we're trying to decrement the local ref count again. So you want to move the increment from the local ref count to the global ref count, right? So that all the other shared pointer instances are also, all the other threads are also aware of it. But this we can do in a CAS loop. So we can say, okay, we modify the local ref count, and then we're trying to modify the global ref count and reverting the local ref count. But if any other thread has modified the state in the meantime, we're just gonna repeat. We're gonna try again. So we're gonna do a CAS loop, right? Compare exchange. And this is kind of the idea. And we try to do this until we succeeded, basically, until we got to increment the global ref count without any other thread getting in the way. So we're gonna have a CAS loop in there. And this is basically the idea. And I'm just going to show quickly how it's implemented, how the load is implemented, because we have load, store, exchange, and compare exchange. I'm obviously not going to show the implementation of all 4 of them, because then we would be looking for an hour just at a wall of code, which I don't really want to do to you. But the load is actually the simplest one, but it does kind of contain this basic idea. So if you understand the load, you understand the idea. So we have our counted pointer here, which is the control block pointer and the ref count. So we have this atomic. We have an atomic member of those. We make sure it's lock-free. And then here's how we implement the load. The first step, as I said, is incrementing the local ref count. Annoyingly, because it's a double width variable, there's no double width increment. So we need to do this in a CAS loop as well. So we kind of have to increment the local ref count, but also making sure that the control block pointer hasn't been modified by another thread in the meantime. So that's why there is this like if compare exchange weak loop going on here. But all this does in the end is to just increment the local ref count. So now once we have that, we have a new valid state for our local shared pointer instance. So we're going to make a copy of that. And like if we succeed, this is the thing we can return. This is like the new state of our shared pointer with the incremented ref count. Now we can increment the global ref count. This is the next step. We can increment the global ref count. So we're just going to go into the control block and increment it. And now we're like, hang on. Okay, so now we need to decrement the local ref count, right? And then we're good. Then we have effectively incremented the global ref count. But we can't just go ahead and do that because we need to make sure that no other thread in the meantime has done anything, right? So we have again a loop. We have again a CAS loop here. where basically we say, okay, we are going to try to decrement the local ref count. You see this minus minus local ref count there. And then if the state of the whole thing with the control block pointer is still the same as before, then we're good. No other thread has modified this in the meantime. However, if they did, then we need to go around the loop again. And there's another case which we have to handle, which is if somebody changed the control block pointer itself. It means that another thread has assigned into this shared pointer instance. And that means we were not supposed to modify the global ref count because it's not pointing to the same object anymore, right? So we need to subtract that again. And so we're going to end up in this CAS loop. So if you're the only thread, then we're just going to fall through and do these three things in order: increment, increment, decrement. But if there's another thread, you might be looping for a little bit. But because it's a lock-free algorithm, you might fail on this CAS loop, but if you do, you know that another thread has succeeded doing this, right? So you never end up with a situation where you're just waiting on a mutex and you have no idea how long it's going to take until the system can make progress. But you have this lock-free guarantee that at least one thread will always succeed in the loop and get to update the shared pointer, and your whole system can move forward. And then in the end, we just return the new state of the shared pointer, and then we're good. So this is basically how it works. Which means each operation on the atomic shared pointer, each atomic access has at least 3 atomic operations, right? Because you have this like local ref count, global ref count, local ref count. If there's contention, if there's multiple threads trying to do this at the same time, then on the same shared pointer instance, then you're not going to have 3 atomic operations, but you're going to have more because you're going to be looping on these, right? So that's definitely going to be slower than a mutex if there's no contention, because acquiring a mutex, if you have no contention, is very quick. Whereas here, in the best case, you still have these 3 atomic operations if there's no contention. So that's going to be a lot slower. However, if you have high contention, if there's lots of threads trying to like pound this atomic, then the lock-free case is going to behave much better than the mutex. So that's the basic idea. The Folly implementation adds something on top of that. They do this thing called ref count batching, where instead of doing this like increment, increment, decrement every time, they kind of pre-increment the ref count to a certain amount k, which is higher than the number of threads you expect to be touching this at the same time. And then basically every time you access it, you just like bite off another pre-incremented kind of ref count, right? So basically you don't have to touch the control block. So you basically pre-allocate, like allocate is now not memory allocation, but kind of allocating like a ref count. So you pre-increment them, so you have some ref counts that you can hand out and just use. And so then when a new thread accesses it, you just like decrement the local ref count until you reach some threshold, like k divided by 2 is one possibility. And then you're like, ooh, I'm running out of pre-incremented ref counts, so I'm going to need to go to the control block and get some more global ref counts now. But you don't have to do that every time. You just do that once some threshold has been reached. And you can actually optimize that as well, like exactly how this algorithm works. You can kind of tweak it depending on what your scenario, and it's very interesting. Can talk for a whole hour about that. I'm not going to do that now. But you can save some atomic operations this way. The trade-off here is that use count, which is a member function of shared pointer, now basically becomes useless because you don't have a meaningful ref count anymore. You just kind of pre-increment the ref count to some high number, so it's just going to contain some high number. You can't reason anymore about how many, like what the ref count actually is. And this is kind of a typical thing for these kinds of classes. Like the more you try to optimize them, the more genericity you lose. So if you do the ref count batching, you don't have a member function anymore that returns the current ref count, which you probably don't need. You only need to know if it's 0 or non-zero, basically. Or maybe you need to know if it's 0 or 1, you're the only one, or if there's more threads. That's all you need to know, typically. But if you want to do more optimizations, you lose more stuff. For example, Ferdow's implementation uses an intrusive approach, which is not the same API anymore as the generic shared pointer. So now you have intrusive pointers. You can do more optimizations, but you lose more genericity. And then you can tweak it for your particular data structure that you're using. And then again, you can get some speed up, but you lose even more genericity. So this is kind of the typical trade-off. Here we're trying to implement kind of the generic atomic shared pointer kind of as a starting point, right? This is how the algorithm works. This is a generic version that is just always going to work, and you can just use it in your code. You don't have to like design your own log-free data structure or whatever. You can just use that. Anyway, so we've done all this. It looks like we have a log-free atomic shared pointer now, right? So we succeeded. This is hopefully convinced you by showing you this code that this is implementable, right? I haven't walked you through the complete implementation, but hopefully I've convinced you that it's implementable. Is it though? So the problem is, we were assuming that this is how a shared pointer works. This is not the whole truth, right? This is a very, very simple shared pointer. This is not how std shared pointer actually works. Std shared pointer has a lot more features. First of all, it supports weak pointer, so it has a weak count as well, which you need to break cycles. You don't really need that if you're dealing with a pointer to a const object, but in general, you have a weak count. Shared pointer also supports a custom deleter, and it also supports a custom allocator. Now, none of this is a problem because all of the stuff is in the control block, and there's just one control block. You don't have to worry about this. This is not part of the state of every individual shared pointer instance. So that's not a problem. But there's another thing which is a problem, and that's this thing. Shared pointer also contains a pointer to the object itself that it's pointing to, which may or may not be the same pointer as the pointer in the control block. And that's the thing that makes it really complicated. Why is that there? Well, shared pointer has a thing called the aliasing constructor. How many of you have used this? Okay, a couple people. Basically, what the alias constructor does is you can have a shared pointer that's managing the lifetime of one object, but actually points to another object. And this is really useful if the other object it points to has the same lifetime of the object you're managing. For example, it's a member of the. So you can have this kind of thing where the shared pointer is managing a pointer to a widget, but then it's actually pointing to a member of the widget, this like int j here, right? So if you dereference it, you get the j, the integer, but then if it goes out of scope, the thing that's going to be deallocated is the whole widget. This is maybe a little bit of an exotic use case. I haven't actually used this in production ever. I know that a few people have used this. It's not like it never happens, but it's a rare case. But there's a much, much more common case which we need to account for, which is this. This is a lot more common. I bet most people who use shared pointer, like as soon as you have polymorphism going on, you will run into this. You can have a shared pointer to base, but the object it's actually pointing to is a derived class, right? And you need to make sure that if you deallocate the object, you call the right destructor. You call the destructor of derived, right? Otherwise, you get slicing and everything is really, really horrible. So this is actually a very, very basic use case that you just need to support if you want to implement a shared pointer. And now we have, so base and derived, they don't necessarily have the same address, right? You can have multiple base classes and stuff like this. So in general, a pointer to base and a pointer to derived will point to different addresses, even if they're pointing to the same object, right? And this is what makes it really complicated here. Because now you have a pointer to base, which lives in the shared pointer, and you have a pointer to derived, which lives in the control block. Those are two different pointers. The pointer to base is per instance, so it needs to be in the shared pointer. It can't be in the control block, right? And now you need to modify not only the control block pointer and the local ref count simultaneously, but also this other pointer, you also need to modify that simultaneously. So you need to modify all three simultaneously. We can't do that. Like there's no triple width compare and swap on any CPU I'm aware of. This is just not a thing. So you just can't do that. How do you get around that? Well, the kind of the three open source implementations that I can look at, they're doing three different things. Anthony Williams' solution does this. He says, okay, we can't store a pointer to the aliased object, but we can store the actual alias pointers into a separate data structure, and we can store an index into this data structure. And then we can cram this index and the ref count together into one integer. Because you don't, like if you're on a 64-bit, it's probably enough if you have 32 bits for the ref count and 32 bits for the index. So you can cram them into one 64-bit integer, and then we're good. We have two integers again that we're storing. And the way this works is that for every new alias shared pointer that's using the same control block, you have a new slot there, and you have three slots that are kind of pre-allocated. They're part of the shared pointer. So, and if you have more shared pointers which point to different alias objects, you're gonna basically push back into this data structure. and you're going to create this kind of in blocks of 3. And the way this works, obviously, it all needs to be atomic, lock-free, thread-safe, and everything. But this is such a simple data structure that you can do it. It's the only thing it supports is pushback and find, and that's it. So it can only grow, it can never shrink. And if you make it that simple, then you can implement this kind of helper structure here with in like 30 lines of code just with some atomic integers. It's kind of easy to do. So he has this like helper structure here. And if you have more aliased pointers, you're just gonna push back into this thing, and you're gonna allocate more of these like blocks of 3. There's a problem here though. The problem is, if you do this, that's memory allocation. Memory allocation is not lock-free, right? So you lose the property that the whole thing is lock-free. And actually, you potentially need to do this on every store, on every exchange, on every compare exchange. It's an edge case, right? If you're using like different aliased pointers with the same underlying object, it's kind of a bit of a weird edge case, but you got to support this. If you don't, it's not going to be lock-free, so you can't claim that your shared pointer is lock-free. And indeed, Anthony Williams, we discussed this on Twitter, admits then, yes, my implementation needs a lock-free allocator, otherwise it's not lock-free. And the lock-free allocator is, it's a pretty complicated beast. It kind of constrains quite significantly like what you can do with your system. You need to somehow, it's not applicable like in every use case. If you're like Facebook or Google and you have a big server and you have like your own allocator going on there and you control the world, you can do something like this. If you're doing like stuff that like what I have been doing for like a decade of my career, is you implement audio processing software that runs on a laptop or a phone. It's like an audio plugin that runs somewhere. You can't put a lock-free allocator in there. You're like a plugin that runs on a host, and you have only that much memory, and like you can't do this, right? So basically, this whole algorithm becomes not viable. I have a suggestion. I have a suggestion how to fix this, which is we can move the allocation from the atomic shared pointer into the shared pointer. So now instead of allocating whenever you do like an atomic store, you allocate already when you construct the shared pointer aliased, the aliased shared pointer. This is when you allocate. And then if you put that into an atomic shared pointer, it's just like an atomic copy. You just have to copy that integer, and you don't have to allocate anything anymore. The problem with this is that it's overhead for every aliased shared pointer, right? Every time you create a shared pointer that has an aliased constructor or is like a pointer to base, which points to the right, you're going to have an extra memory allocation there. Well, there is actually something even more clever that you can do, which is, observe that if you have an aliased pointer, typically the pointer of, for example, base or derived, or the pointer of like an object and like a member of the object, these are the typical use cases, they're not going to be very far away from each other, right? So you're going to be pointing into the same object. So what you can do is you can compute the pointer difference between the object pointer and the aliased pointer, and that difference typically is not going to be very big. And if that fits into 32 bits, and I really hope it does, because I really hope you don't have one object which is bigger than 4 gigabytes, you can just store that pointer difference directly instead of the index, right? It fits into 32 bits, so you can cram it into the second 64-bit of your 128 bits together with the ref count. You just store the pointer difference directly. And if you have this weird edge case where your aliased pointer and object pointer are more than 4 gigabytes apart for whatever weird reason, then you can still use the extension list, so which is this auxiliary data structure that Anthony Williams invented. But it will happen extremely rarely, probably never. And only in that case, you will have to pay for this allocation in the shared pointer, but you can put it in the shared pointer. You don't have to put it in the atomic. And then you can also use one of the alignment bits to indicate which methods you're using, and then your atomic shared pointer is lock-free. This is cool, right? Yes. So do we now have a lock-free atomic shared pointer? Have we done? Turns out there's another problem. This whole thing relies on double width compare and swap actually being available. Is that actually the case? And again, I looked into this, and again, I got very conflicting information from different people. And there were some people, kind of the hardware people, that were saying, oh yeah, double width compare and swap, it's you get it on every modern CPU if you're dealing with like Intel or ARM or something like this. Like, yeah. All the modern CPUs, they have this instruction, no problem. And then on the other hand, I have, C++ people, and they were saying, no, you can't do this portably. Like, this is not, it's like some platforms maybe support this, but in general, double with compare and swap is not a thing. You cannot rely on that being there. I was like, huh? Like, what's actually going on there? So I did a lot of research. I wrote it up in a really long blog post. I don't have time to basically go over all of this now, but if you're interested, you can read it. It's on my blog, timur.audio. I'm going to give you like a very quick summary of this. Basically, the first question, do our CPUs support this? And if you're talking about desktop or mobile or something like this, you're going to be talking about 32-bit Intel, 64-bit Intel, 32-bit ARM, and 64-bit ARM, right? These are kind of the platforms that I'm interested in. If you're on some kind of embedded platform, I don't know, I'm not the expert. You are the experts, you tell me. But like on these CPUs, they all support this. 32-bit x86 has this instruction compare exchange 8B, 8 bytes, 64 bits. The 64-bit Intel version has compare exchange 16B, which is available on every x64 chip since, like, there's some very old like AMD chips from 2008 and before that don't have that instruction, but they're very old. Everything since then, you can rely on that instruction being there. Actually, Windows doesn't run if you don't have that instruction. Since Windows 8.1, like, Windows doesn't even install if your CPU doesn't support this instruction. So it's there. And the same story on ARM, depending on like what version of ARM you're on. Like the very newest ones, I think they also have one instruction now for this kind of, and then kind of older ARM chips, they have this other thing which is called load link store conditional, which is a different way of basically doing something that is the same thing. So it's there. The instruction on these platforms is available. Something that people have said, yeah, but it's slow. And then I looked into this too, and I found, well, not really. On x64, double with compare and swap is about twice as slow as compare and swap, which makes sense because it's doing double the work. But it's not 10 times slower or anything like this. You don't get an abysmal performance hit. And actually, I tried this also on the oldest x64 computer I could find at home, which was a Mac Mini from 2012, and I got the same numbers. It's only twice as slow. It's not 10 times as slow or anything like that. And actually, on modern ARM chips, it's not even twice as slow. It's more like 1.5 times as slow. So you don't have a catastrophic performance hit if you use this. But the bigger and more interesting question is, well, does it work with the standard library? Does it work in C++, where we have stood atomic? In other words, is this assert going to pass? And that was me when I was looking into this. I was like, well, your CPU supports this. Surely stood atomic is going to support that too. No. And again, I wrote it up in this blog post. I'm going to just quickly show you like the table, basically. You have the different CPUs and like the different compilers. So on macOS, like Apple systems, macOS, iOS, everything's fine. All of their Apple Clang supports it because all of their platforms require that to be there. Clang on Linux is kind of a bit more of a mixed bag. You need to pass this compiler flag to make it work and also align it on 128 bits. And then if you use that compiler flag, you have like 2 different versions of stood atomic floating around in your binary potentially. So you get ODR violations. It's hairy. And then on GCC, and when GCC is really sad, on the 64-bit versions, both ARM and Intel, which are the 2 platforms that we really need if you want to do stuff on modern consumer hardware, like this laptop or my phone, it's not available. Basically, the instruction is there, but in C++, if you use the atomic, it's not going to use it. It's going to fall back to a mutex implementation. And the reason for that is basically ABI stability, like, and backwards compatibility. I think what happens on GCC is that they actually want to support these like pre-2008 AMD chips. And what happens on Windows is, well, they just have stood atomic from however many years ago, and they would have to modify that. That would be an ABI break, so they don't do that. They do that with stood atomic ref. That's a new thing in C++ 20, so that supports double with compare and swap, but stood atomic doesn't because backwards compatibility. So that's another one of those cases where the standard committee just, or the kind of implementers choose basically backwards compatibility over performance, which I think is just not a good solution for most people. It's very sad. So what can we do about this? Well, we can implement our own std-atomic. Oh, and by the way, like GCC libatomic, this is what this falls back to, and on 64-bit, that doesn't help us either. Like they have these like library calls and they have these like CPU intrinsics, but it will also, like, you have no guarantee that it will actually use the instruction. It goes somewhere into libatomic, and that probably will add mutexes. You have no guarantees whatsoever. So you can use your custom implementation of libatomic, basically, which is something that I don't know how many years that would take to write, but I would certainly not be able to do that. There is an implementation in boost atomic, which maybe you can use, which gives you this. Or the other solution is don't use double with compare and swap. And actually, this is kind of what you end up doing. Don't use double with compare and swap. How do we implement this without using double with compare and swap? Well, actually, there is a technique. It's called packed pointer. And that's the one that's used by all the implementations except the Anthony Williams one. So Vladislav's implementation uses it. The Folly Facebook implementation uses it. It only works on 64-bit. And basically what it does, it exploits the fact that 64-bit Intel doesn't actually use all the 64 bits to store an address. It operates on a 48-bit address space, which means that, first of all, you have a few bits here, which are the alignment bits, which you can use for, like, it's either 3 or 4 of them, depending on what the value of std max align t is. But more importantly, you have 16 bits in the front, which are just not used for the address at all. They're not used. So you can put your own, you can put your ref count in there, right? And you have 16 bits, so that means you can have up to 65,000 threads, which hopefully is more than anybody needs. And so you can cram your ref count in there. So Intel actually now went to, I think, a 57-bit address space. So then, like, it's more complicated. But actually, and there is a Linux kernel that supports this, and there is also hardware, I think, that now supports a 57-bit address space. But actually, surprise, Hiram's law, you know, there are lots of programs out there depending on those 16 bits being unused. So this whole 57-bit address space thing is kind of just for in kernel space for now. And like, if you have a user space application, it's an opt-in, and by default, it's still only going to use the 48-bit addresses. And the same story on 64-bit ARM. Again, they have a 48-bit virtual address space, and now you have a thing where you can use more bits, but again, that's opt-in, and by default, you can rely on those 16 bits being unused. And I don't think that's going to change, at least in the next decade, because we have this, you know, software that already relies on that being there. Well, let's see. But for now, I think we're good with using those 16 bits there. And then if you do that, you end up with something like this. So this, now we have, instead of the kind of struct that has a pointer to a control block and then a ref count, you have this slightly more complicated structure, which is the atomic packed pointer, where you have just one atomic 64-bit integer. That's your value, and that now contains 16 bits of ref count and 48 bits of address. And in order to get the pointer out or to get the ref count out, you kind of have to do offset and mask. You kind of have to either shift the 16 bits out or mask the 48 bits away. Yeah, if you store, you have to do them in reverse. I'm sure you can imagine what that looks like. This one actually, it's kind of a hidden reinterpret cast here, because like you're doing like an offset on an integer, and then you're kind of returning that as a pointer. But actually, it turns out this is fine. This is like pretty much the only use case where reinterpret cast is actually okay, because there is actually an object alive at that exact address that you're going to return in the end. So we're good. And now we're here. So we have a ref count and our pointer to the control block crammed into one 64-bit variable now, which is great. We still have the problem of the aliased pointer. And now there's definitely no space to put the aliased pointer anywhere. So how are we going to solve that? So Folly has one solution, which is they kind of wrap this. They have another level of indirection, right? They wrap this into another thingy. So you store a pointer to a thingy, which then points to the control block, which in their case is just another shared pointer, basically. Problem. This is again a memory allocation, so it's not lock-free. And if you're Facebook, that's probably fine, because you have your own allocator that handles all the allocations on your server, and you you know what's going on there. But if you want to run an audio plugin on a laptop, that's not good. So again, my suggestion is we can move the allocation from atomic shared pointer into the shared pointer constructor. So the atomic one is going to be lock-free. Now we still have this overhead for every aliased shared pointer. Every time you use the aliased constructor, or you have a shared pointer to base and it's storing a derived, you're going to have an extra memory allocation, and this time there's no way to get around that. That's not going to be an acceptable trade-off for people who just want to use the shared pointer without the atomic part. So that means we definitely can't build this on top of std shared pointer. We need to use our custom shared pointer now. But, you know, if you want to use an atomic shared pointer, that's probably okay. And we can make it lock-free. It's just that Facebook hasn't done that. And the other implementation is the one from Vladislav, and he also uses the pack pointer technique, but he basically just doesn't handle that. So if you take his implementation and you create a shared pointer to base and give it a pointer to derived, it just crashes. He just doesn't handle that case at all, which is unfortunate. But it's not a production-ready implementation. So actually here, this is a little overview of all the different implementations that there are that are open source. Portability, Anthony Williams relies on double with compare and swap. That's not in general portable. Vladislav works everywhere in 64-bit because he uses the pointer packing, so that's good. Folly actually only runs on GCC because they built their thing on top of GCC lib std C++ shared pointer, right? So they actually have this thing where, you know, you have this trick where you use explicit templates installation to like get access to a private data member of a class. I don't know if anybody has heard about that trick, but that's what they're using. That's really evil. And that obviously only works for this particular standard shared pointer implementation. So it only works in GCC. Is it actually lock-free for the aliased pointer case? None of them are. Like Anthony Williams has this like auxiliary data structure which allocates. Vladislav just doesn't handle that, and Folly also allocates. Is it standard conforming? Anthony Williams is almost there. He pretty much has the whole interface of shared pointer there. Vladislav is very, very rudimentary. There's lots of stuff missing. There's no exchange. Lots of the constructors are missing. It's kind of just a half-finished implementation at this point. Folly is pretty good. They don't support weak pointer. There's a few other things they don't support, but it's mostly the functionality of shared pointers there. And then, obviously, most importantly, is it production ready? Well, Anthony Williams and Vladislav, both of them are just proof of concept. They're not really finished production ready implementations. I found bugs in them, in both of them, within 5 minutes of using it. Like something crashes, something doesn't work. The Folly one implementation is the only one that I'm aware of that's both open source and production ready. That actually works. They have been using it for years and years. That's where we are today. Okay, I have a couple more minutes, maybe very quickly run through the benchmarks here. What I was doing here is I was trying to see how this performs. So I did this very crude thing. It's not a good way to benchmark this. I really need to figure out a better way to do this. Basically, I have a bunch of threads, and they're just pounding this atomic shared pointer. So I just have a cast loop here. They're just like trying to update the value there. And then I have this one thread, and the number of those threads is kind of variable. And then I have one thread where I'm just doing one atomic load, or one atomic store, or one atomic compare exchange, or one atomic compare exchange in the loop until it succeeds. And I'm going to see how long that takes. And I'm kind of doing two things at the same time here. I'm measuring just kind of contention on an atomic in general at the same time as measuring the actual shared pointer. So it's not a good way to benchmark this. If anybody has an idea how to benchmark this better, please let me know. I want to know. These are the results. Basically, this is on Apple Clang. This is one of the two compilers where I can compare multiple implementations. So I'm comparing the standard one. I just used the freestanding because Clang doesn't have the atomic shared pointer. It only has a freestanding function, so I wrote a wrapper around it. And I'm using that. That one uses mutexes under the hood. That's the black lines. And then we have Anthony Williams, which uses double with compare and swap, and Vladislav. And you see this typical thing here where the mutex version, on average, that's like the star, is actually faster. It's actually a lot faster on average. But then if you look at the worst case, which is the top of the bar, that's where the mutex one is really bad, because once in a while you get stuck on this mutex forever, and you can't reason about how long that's going to be. So you're not limited in like how long you might wait on there. And so the lock-free versions, both Anthony Williams and Vladislav, they're more costly on average, but the worst case is orders of magnitude better. And that's really what you want if you're doing lock-free programming. Interestingly, also, Vladislav here is about 2 to 3 times faster. One reason is he doesn't use double with compare and swap. He uses the peg pointer. And the other reason is if you use peg pointer, then the local ref count increment, you don't have to do the cast loop there anymore. Remember, that was the first step of the atomic load. You can just do one atomic, add one atomic increment. So that becomes faster as well. If you look at the other operations, so that was the load. If you look at store, compare exchange, and compare exchange in a loop, Vladislav has a kind of an unfortunate implementation of store. It's not very efficient. Anthony is better there. That can be implemented better. Compare exchange is kind of the same as load, and then doing compare exchange in a loop is actually really bad. You should be avoiding this if you're doing a lock-free atomic shared pointer, because now the compare exchange itself is a cast loop, and then you put the whole thing in an outer cast loop as well, and that's just going to have bad performance. So that's not really better than the mutex version, so you should avoid that. And this is the other compiler where I can benchmark stuff, which is GCC, because Folly compiles on GCC and Vladislav compiles on GCC. Anthony doesn't, because GCC doesn't do double with compare and swap. And here, it's a very similar picture, really. Right. That's pretty much it. Future work, I want to do better benchmarks. And the other really important thing is, obviously, I'm working on my own implementation, because I want to solve these problems. Remember, this is kind of where we are today with the 3 open source implementations that are available. What I want to do is I want to be more portable by actually letting you choose whether you want to do double with compare and swap or not. And potentially also using like a custom atomics in there, so you can force it to use double with compare and swap if you want to, if you know that your CPU supports it. I want to solve this problem of the lock-free. I want to actually make it lock-free, like for the aliased shared pointer case, which none of the implementations are doing that, which I showed you how to do that. And I want to make it standard conforming as well by basically supporting the whole API. And hopefully one day I will actually have this in a production ready state. It's unfortunately right now not there yet, so it's not public yet. So I also want to experiment a little bit further with some optimizations, and then once my implementation is ready, which hopefully will be later this year, I will publish it on GitHub. So right now it's unfortunately not ready yet, but I'm working on it. Hopefully in a few months or even faster. I don't know how much time I get to work on this. It will be on GitHub. And yeah, I actually already, this is my last slide. I actually know, I can already tell you where it's going to be when it's going to be on GitHub. It's going to be in this repository. This is a side project that I started with a friend of mine, Fabian Rengiles, just a few weeks ago. And this is the first time I'm announcing this. We started this little library, which is called Krill. Krill stands for Cross-Platform Real-Time I/O and Low Latency Library. So it's going to contain all these little utilities for like lock-free and low latency programming that we have come up with over the years. Currently, it's very raw. It just contains one class at the moment, which is this spin lock with progressive backoff that I have done another talk about. That's all there is. There is no documentation yet either. But this is where we're going to be putting all these little utilities, and this is where the atomic shared pointer is going to be as soon as I've finished implementing it. So watch this space. And with that, I'm done. Sorry for overrunning by 3 minutes. I hope you can forgive me, and I hope you enjoyed the talk.